example 2, and this one states, yeah, this is on the sketching the tangent vector. So for the curve listed below, find the derivative r prime of r vector prime of t, and sketch the position vector r of 1 and the tangent vector r prime at 1 at t equals to 1 there. So there's the function right here. So if the vector function r of t is equal to square root t times I plus 2 minus t times j, so the j vector, unit vector. All right, so let's take a look at the solution. So we have, so let's first get the derivative. So r prime of t, this equals to, this equals to, well, this is, now we take the derivative of square root t, and recall that square root t, that's just equals to 10 to the, t to the 1/2, so we would bring the 1/2 down. So we would bring the 1/2 down and then subtract it by 1. So 1 over 2 minus 1, so in other words 2 over 2, that becomes negative 1 over 2. So that's just going to be equals to t negative 1 over 2, I, like this. And now this one here, the derivative, this is equals to, well, 2, 0, and then this one's negative, derivative of t is, negative t is negative 1. So we have just negative j, like that. So in other words, this equals to 1 over 2, and then square root, yeah, let's put a square root at the bottom, so I'll put this like this. 1 over square root t, like that. This is going to be I minus j. All right, and let's box this in like that. And now we could just solve for, so we need to sketch the position vector r1 and the tangent vector r prime 1. So let's just plug those in to see what the values are first. Yeah, so what we get is, well, r, put an arrow like this, r prime of 1, this equals 2, we'll plug that t inside. So 1 over 2 times square root of 1, that's just 1, so it's just 1 over 2. Yes, this becomes 1 over 2. I vector minus j vector, like that. So that is this one here. So now we have the derivative, and we have derivative at 1. And then lastly, let's get the point at just a regular vector there. So r1, this equals 2. Let's plug these values. So that's going to be square root of t. So basically square root 1 I plus 2 minus 1 j. So this equals to, well, I, and this is going to be plus j, like that. So there it is. All right, now let's go further. So so the curve r vector t is a plane curve, and elimination of the parameter from the corresponding parametric equations gives. And what I mean by the plane curve is because, well, there's no z component here. So basically, the z components can be all infinite values. For example, if this is just a random line like this, but then if it's in 3D, you have to account for all of the z values of it, which are infinite. So you're basically going to get a surface like this, something like that. Anyways, so we need to sketch this out. So we're going to sketch it. So let's get rid of the parameter t, because these are just parametric equations inside, and then basically we'll have a function in terms of y and x only. So let's write this down. So we have r of t. Let's just write the whole thing out. This is going to be square root t I plus 2 minus tj, like this. That's this one right here. 2 minus tj, like that. So now this equals to, now basically the parametric equations are, this is just saying, well, we have x is equal to square root t. So basically write these out as parametric equations. Y component is going to be equal to 2 minus t. So in other words, if this is t like that, so I'm going to square both sides. So I will square this. I'll just square this. I'll just square this. Square this, we end up with, well, x squared is equal to t. So in other words, t is equal to x squared. Throw that inside, we get y equals to 2 minus x squared. Yeah, so there it is. So y is equal to 2 minus x squared, which is the parabola. or I'll just put this together. So then we get y is equal to 2 minus x squared. So we have a parabola, and it's going to be a surface because you have all values of z. All right, so and now we're asked to solve for, again, sketch the position vector r of t and the tangent vector. So r prime of t. So let's draw these out. So in the figure below, we draw the position vector r of t, r of 1 equals to I plus j. That's just this right here, starting at the origin, and then the tangent vector r prime of 1 starting at the corresponding points 1, 1. That's yeah, they're basically starting at this point right there. Yes, in other words, position vector, we start from 0, the origin, to it at 1, 1, and then the tangent vector is at tangent at 1, no, at this 1, 1 point. So we draw the vector from there. So let's draw this out. So and we also know that the curve is this y equals 2 minus x squared. So if we graph this out as just the x and y axis. Okay, there's the x, there's the y, like that. So now, yeah, so what I'll do is, so now it's going to be the curve 2 minus x squared. So in other words, it's going to be an inverted parabola. So we have the 2. It starts off, when you plug in x0, we get y is 2. So it starts off here. So there's our 2 value. And then it goes all the way down. And for example, you could say that when, well, actually, we don't even need to do that because it's a minus x squared. So we're going to be minusing. So in other words, it's going to be an inverted parabola like this. And we're only going to look at the positive x value there. And this value should be, actually, if you plug in y0, y0, so we'll have this 2 on the other side, so square root 2. That's a square root 2 there. So we have this, and now the next point is draw the position vector. R of 1 is just at 1, 1. So that's going to be at 1. Let's say we have 1. This is going to be at the halfway point. 1, 1. Let's say it's over here. And here I quickly fix it up to make it more of a parabola, less of a, like, a spherical shape. But anyways, so this is the point 1. So point 1, 1 should be across here. Yes, this is at point 1, 1. This is at 1, 1. So this is the point 1, 1, like that. So this is the vector from here to here. This is the r of t vector, like this. 1, like that. And now the position vector, I mean the tangent vector, we're going to start from here. I'm going to draw this in red. And that is going to be, well, let's look at this. It's going to be 1/2 I and then minus 1. So that means we go to the right 1/2. So if this is 1/2 would be somewhere around here. So let's say if 1 is over here. So let's make it, and then so it goes halfway here, and then it goes down by 1. This right here. So this is positive to the x-axis, half of 1.5, then minus 1. So 1 on the y-axis. So it goes down 1. So it's going to be across here. Yeah, but this is at the halfway point here. So here all the way to 1. So it's going to be something like this. It's a bit off. But anyways, that is how it should be. Yeah, so like that. This is actually a bit more circle. It's actually closer here. So yeah, so that's the red one there. So yeah, it looks pretty legit there. So there is our vector. I'll draw the arrow. It's going to be, again, there's the directions like that. And this is going to be, this is markers for just for my own sake. This is going to be at r prime of 1. Like that. All right, and going further, notice from the above figure that the tangent vector right here, this r prime of 1, points in the direction of increasing t, and that's because well, we know this equation of this this curve is y equals 2 minus x squared, where x squared is just t. So as you increase x is going down, so it's increasing t is going downwards, and this is in the direction of it, and it turns out it's always in the direction of it, and that's basically C exercise 1 at the end of this video. It's very interesting on that. Yeah, and basically this tangent vector is always in the direction of increasing t. So, and also to illustrate this, and also that the regular curve right here in 3D is a plane curve, as I mentioned right here. So r of t is a plane curve. I'll graph it out in GeoGebra to see how that is. So here's how the plane curve looks like in 3D using GeoGebra's 3D graphing calculator. And also I also added a vector right here, so you could also play around with the tangent vector there. Now note what I did. Was, well, here's the plane. So if we have y equals 2 minus x squared, but if you draw them 3D, that means the z value is going to be infinite. So you basically draw your parabola, and then you draw it for the entire up and down. And hence that's why it's a plane curve like that. And here I also drew the curve right here, and I used a instead of t, and the reason is when you use a, you could use it as a variable. You can't use t as a variable for some reason in GeoGebra, so I just used a. So this is just the curve a, square root a, or a to the power of 1/2. That's just this part right here, then plus 2 minus t, or 2 minus a. And then that graphs it out, so you can graph it out at the bottom like that. And furthermore, what I did, this vector right here, you could use the vector equation. So this is the beginning point, begin, and this is the end point. And the way I did this is basically I inputted, this would be the input of the curve. So this is the exact same equation right here. This a1, a to the power 1/2, that's right here. 2 minus a, 2 minus a. And then 0 for the z component, just because it's just flat there. And then the second part here is the end point. Well, the end point, I wanted basically the, yeah, it's basically at the tip of the vector right here. So this endpoint, well, what I have to do is I have to add this r vector plus the r prime vectors, and that's what we have here. So basically, I have this is a1/2, and then plus 1 divided by 2, then square root a, or that's this part right here. This is the r prime vector. So I just added no, this one right here, and then minus 1. So there. So then. So basically, and then I would go 2 minus a, and then minus 1. So I'm adding those as the ending vector, and then basically you can get that there. But anyways, I'll click that, and let's go and see how this looks like. I think I have it opened already, right here. So I have it opened right here, and there is the curve. It's pretty epic stuff. And you could see that. And now this one right here, you can move it, and it's always, as you change the value of a or t in this case, or t or a in this case, you can see it's always tangent to it. And there it is, and then it becomes basically, because it's parabola, it flattens out like that. So what I'll do is, I'm going to go like this, all the way across here. Yeah, so you can see that there's a bit nicer there, and then you can also play around with the plane curve. There's a surface on there, there's a surface, there's a plane, and yeah. So yeah, epic stuff there.